Let's begin with the widely used data types and their sizes. The first column shows the C data types. The second column shows their sizes on 32-bit Intel x86 processor, and third column shows their sizes on 64-bit x86 processors. The char data type is a 1 byte on both 32-bit and 64-bit x86. Short is 2 bytes on both. Int is 4 bytes on both. Interestingly, the long is 4 bytes on 32-bit x86 and 8 bytes on 64-bit. Long is 8 bytes on both. Float is 4 bytes on both. Double is 8 bytes on both. The most interestingly and importantly, the pointer data type is 4 bytes on 32-bit and 8 bytes on 64-bit. This is because the pointer data types are supposed to hold the memory address, and memory address size matches the bitness of the machine. Let's think about why the size of data type is important when we program. Here is an example. We declare unsigned integer variable TMP and initialize that with 200 times 300 times 400 times 500, which is 12 million, and 2CB417800 in hex. The problem here is that this number 12 million needs more than 32 bits to be stored. Unsigned int variable can hold only 32 bits. If you print the value of variable TMP, you will see only 8 digits of hex CB417800 without leading to. This means that the variable TMP is initialized with a much smaller value, which is definitely not what we intended. The machine has a word size. It's the size that a machine is designed for. It's usually the size of a memory address or size of a pointer or register. The word size is 32-bit on 32-bit machine and 64-bit on 64-bit machine. It also usually matches the size of integer data type. The 32-bit machines use 32 bits or 4 bytes words, which limits virtual memory address to 4 gigabytes, which is 2 to the 32. Such 32-bit memory address space became too small for memory-intensive applications, so we moved to 64-bit machine about 15 years ago. The 64-bit machines use 64 bits or 8 bytes word, which limits the virtual memory address to 1.8 times 10 to the 19 bytes, which is huge. The 64-bit x86 machines use only 8-bit address, which is 256 terabytes, not all 64 bits. This is just a practical design choice. The most 64-bit machines can also run programs compiled for 32-bit machines and offer perfect backward compatibility. To compile for 32-bit processors, GCC has a -M32 flag. Let's talk about pointers in C and C++. The pointers are variables whose contents are interpreted as a memory address, and they are supposed to point other objects or functions. To declare, we use a star symbol, T space star P, where T is a regular data type and P is a pointer variable name of your choice. For example, integer pointer variable P is declared as int space star P, and float pointer variable Q is declared as float space star Q. We initialize pointer variable with the memory address of other object, and we use an ampersand symbol to get the memory address. For the example on top right corner, to initialize the integer variable p excuse me, with the address of regular integer variable I, we have a p equal ampersand I. I must be an integer variable declared earlier. We can get the value of I by dereferencing pointer variable p. To dereference, we use a star symbol like a star p. The last statement dereferences p and initialize of regular variable j. It's the same as a int j equal I. Here's another example. We have a int x, the integer variable x, and initialize that with the hex 1000, and we declare in the pointer variable p, the int star p, and initialize that with the address of x. And here we assume that x is stored at memory address hex beef, and p is stored at memory address hex 1000. The diagram on the right hand side visualize the declaration and initialization and location. So memory address at hex beef, we have x whose value is 1000. At memory address 1000, we have value hex beef and beef. Alright, the first printf statement prints the address of x, ampersand x. So address of x is hex beef and beef. So hex beef and beef will be printed on the screen. And second printf prints ampersand p, which is the address of p. So it will print hex 1000 and 1000. Third printf statement prints a value of p, which is the address of x, which is hex beef and beef. The last printf statement prints the dereferenced p, which is a hex 1000, which is the value of x. Let's talk about bit-level operations. These operations apply to any integral data type such as long, int, short, char, etc., and view arguments as bit vectors. We have a bit level AND, OR, NOT, and exclusive OR. Here's an example. NOT of hex 41 bitwise and hex b echo. First, we convert them to binary numbers, binary bit vectors, and apply bitwise unary NOT followed by bitwise AND. The same thing for the second example. It has a bitwise OR instead of AND. Self-exclusive OR always returns 0, which is widely used in assembly program when we need to initialize variable with the 0. Logical operations look very similar to bit level operations, but result very different value, and it has a different purpose. For logical operations, we use a double ampersand, double vertical bar, and exclamation mark for NOT. These operations view 0 as a false and anything non-zero as true. They always return 0 or 1. Here we have some examples of logical operations. Again, the key is to view arguments as false or true. Let's talk about shift operations. We have left shift and right shift. The left shift is very straightforward. We simply move bits left by shift amount and fill the right end with the zeros. For right shift, we have two versions, logical right shift and arithmetic right shift. Logical right shift is very straightforward. We simply fill the left end with the zeros. However, arithmetic right shift replicates the MSB, the most significant bit, on the left end instead of zeros. This is to preserve the sign of the number.